What I'm interested to cover in this video is how a low-level view on how virtual methods work. Typically, most of the C++ tutorial I've seen online, they oversimplify how the virtual methods code is generated. So here we are gonna go practically, and we're trying to use some code and see what is the assembly generated and understand why the assembly is generated in this way. The other thing is that we will start by not turning on the optimization, so we see straight away what the compiler is generating for us. And after we try to turn on the optimization and see what the optimizer is doing with the information that are given from the code that we wrote. Before that, we need to talk about the ABI. The ABI stands for Application Binary Interface, and it's a standard that defines the interface between the application and the operating system. What it is doing with the ABI is specify a way to describe how the call to subroutines needs to happen, how the registry, how the parameters needs to be passed, how the call to system calls are working, or how the data layout of a struct works like. In this specific instance, we're gonna look at the Itanium C++ ABI, which is at this address. You can find a reference. So this is the Itanium C++ ABI. In the first case, we are gonna cover the situation when we have inheritance, but we have no virtual methods, and we want to see what's happening here. So we have class B, and this class B is inheriting from a class A. So in this case, if we look the object layout of B, the object layout of B will contain X from A, and then will contain Y from B. So this is gonna be the object layout. And as an example, for the main, I created a simple application that calls F, and we instantiate so B through a pointer from A, and then we call F through getVal, and then we delete it. So we avoid in this case to use share pointers, so unique pointers, because just to make the understanding of the assembly easier. And as we can see from the generated assembly, what we get, it's a call to F directly. We don't go through the virtual table. There is a direct call to F that is in A, even if we are allocating a B object here. So in this case, as we can see, we don't have any virtual table created. Now, in the second case, we're gonna add, in our example, the virtual destructor for the class A, and so we're gonna add the virtual function f. And this virtual function f is gonna be overridden inside the struct B. So now the object layout for B and for A is gonna be looking differently. So we are gonna have as the first byte of the object of A, we are gonna have an 8-byte pointer that is our virtual table pointer, vtable pointer. This is hidden from the user, and the compiler is gonna generate the code to use this area of memory to load the address of the virtual pointer table. So, which is the address where there are the function pointers for our methods, meaning the destructor, This we will look at more in the future, like in a future video, or F. So that's why here you can see that there are these entries for the complete object destructor. And we will have, in the case of object A, 4 bytes for X, but also we have an additional part that is containing the padding, because the object it's padded on the sides of the virtual table pointer that is 8 bytes. Since B has also Y, this padding is not present anymore. And so we have 4 bytes here, 4 bytes here, and then we have still 8 bytes for the vtable pointer. And one thing to notice is that even if we are inheriting, we are not gonna have two entries, two virtual table entries, like two areas to contain the virtual table pointer. We're just still gonna have one area, one piece of memory of 8 bytes that is gonna use to contain this pointer. Let's take a closer look on how virtual methods work in our context, in this example. So the first entry is the offset to top. The offset to top, in our case, it's 0 because we are in a single inheritance, this 0 here. 0 equals single inheritance. Second is the runtime type info that contains the information about the type, and these two entries are always present in the entry. In particular, the offset to top is a 64-bit integer stored at the start of this virtual table that tells the runtime how far to adjust the this pointer to reach the start of the most derived object. The virtual pointer, when it's loaded, doesn't start on 0, but starts on the first entry of the virtual table. So the first overridden function, that in our case is the complete object destructor. Similarly, for A, we have the same similar layout. So still v pointer is gonna point. This is the vtable, this one. And the v pointer, when the compiler is generating the code, is made it such to point the first entry that is pointing the v pointer is the complete object destructor. If you look into the base object constructor, what you're gonna see is that what is happening inside the assembly is that after some kind of a preamble, there is a call to the A constructor, and then there are some operations afterwards. Let's go to the call to the A constructor. In the call of the A constructor, what is happening is that in EDX we are putting the offset of the vtable plus 16, which is the first, if you remember for the previous slide, this is the first method pointer, because 0 and 8, one was containing the offset to the top, and the other was containing the RTTI. Then, after this call here, the second part that is happening is that we are assigning this to the object. So RB -8 on the stack of our function, like here there is a pointer, and this is the this pointer. And after that, RDX is containing this, so here in RDX we move inside the this pointer. So which as we see, this is this. So that this pointer will be equal to object. Sorry, to VPTR. And this is the pseudocode that we see. So the object VPTR is equal to the start of the vtable plus 16, so skipping the first two elements, the first two 8-byte entries, and then the object of x, which is the last instruction, is RIX plus 8. RIX, we say that is pointing to this, so will be this one. This is RIX plus 8. This is pointing to x here, and is going to contain 10. Getting back to B, after A is constructed, the second part is that we need to override the virtual pointer. So to override the virtual pointer, what is happening is that we are gonna, so the compiler is gonna move the offset again of the vtable for B plus 16 to skip the first 16 bytes, which are for offset to top and RTTI, and loads this value. Then, since we have this value in EDX, so from RDX we are copying basically at the start of the object again. So now here we are really overriding, because at this point the VPTR contains the start of the object A, so it's containing A vtable 2, as we see before. But after this call here, we are de facto overwriting the object pointer, virtual pointer, and this is containing now B vtable 2, which is the address of the first entry, the first overridden function in B. And then the last part here is to set y to 30. The stack is here again, this, x, and y, as we saw before from here. All these variable, so all these pointer and variable are contained into the stack. Now, after having described how the construction of the object B works, we can analyze how the polymorphic call mechanism is working in main. So in the first statement, what we are having is that we are storing the pointer that of the object is allocated on the heap inside RIX. And this is the first call, the first statement, how it's mapped to which instruction. The second statement, it's more complex, and this is the real core of the polymorphic call, and it's mapped to this set of instructions here. Since now we need to understand a bit more in details how this mechanism works. So first thing, we need to remember how the object layout is done from the previous examples. And A is basically pointing to the start of the object B in memory, and the first 8 bytes of this object in memory is gonna contain the V pointer. The V pointer is pointing to vtable plus 16. And this is actually what is doing this instruction here. Is basically loading into RIX whatever is pointed by A. So it's loading the v pointer within array X. At this point, since, as we discussed before, this offset to top and RTTI are skipped according to the ABI, we are jumping here at this point. To get to our F, where we want to jump to, we need to add 16 bytes. So that's why there is an add array X 16, which is array X plus equals 16. And the effect of this instruction is to jump here to this point of the table. Inside the table itself, we have the pointer to F. And the pointer to F is what is loaded in the next instruction. This move rdx array X, whatever is contained within array X. So rdx is equal whatever is contained in array X, and what we are saying is that rdx is containing F. So this is rdx equals F. And finally, after all this boilerplate, we can finally jump to the entry point of F through the call to rdx. Interesting to notice here that we have a double indirection call. So we have two indirections. First, we load one time in memory to get the v pointer, and the second time to get the pointer to F. So we first load the v pointer, then we adjust the pointer, and then we reload again in memory. We access again in memory to load the entry of the vtable that we are interested in. What happens when we enable optimization in Clang and GCC? In Clang, if we enable optimization auto with this code, which is not the maximum degree of optimization, what we see is that the compiler is able to optimize out all the virtual tables. So it's devirtualizing all the function call. And understand that at the end, what is returned is just, since we return x plus y, we need just to return 40. GCC instead doesn't seem to find, understands that 40 needs to be passed in EAX, but then it doesn't understand, it's not able to completely optimize out the virtual table for B, like we have seen in Clang. Final thing I want to show you is in Clang how to see the optimization passes. This is quite interesting because we can see which kind of transformation, compiler transformation, allow this kind of aggressive optimization. And if I, for instance, activate the opt pipeline here, we can see what are the passes that are activated. And one of the most interesting one that is deleting quite some part in the intermediate representation is this SROA pass, SROA, that stands for Scalar Replacement of Aggregates. There are also lots of other optimization happening, and maybe I will try to dig more into those optimizations in some of the next videos.